Hey everyone, welcome to the video lecture for Module 1.2.6. This is the final module in Module 1.2. As always, make sure you take a look at the learning objectives here. And today we're going to cover some hormonal interactions and some associated behaviors that go along with that. So we usually study hormones individually, but the extracellular fluid contains a mixture of hormones whose concentrations change daily or even hourly. As a result, cells never respond to only one hormone. Instead, they respond to multiple hormones. When a cell receives instructions from two hormones at the same time, four outcomes are possible. One, the two hormones may have an opposing or antagonistic effects, as in the case of PTH and calcitonin, or insulin and glucagon. The net result depends on the balance between the two hormones. In general, when two antagonistic hormones are present, the observed effects are weaker than those produced by either hormone acting unopposed. Two, the hormones may have additive effects, so the net result is greater than the effect that would produce acting alone. In some cases, the net result is greater than the sum of the hormone's individual effects. This interaction is a synergistic effect. An example is the glucose sparing action of GH and glucocorticoids. Three, one hormone can have a permissive effect on another. In such cases, the first hormone is needed for the second hormone to produce its effect. For example, epinephrine does not change energy consumption unless thyroid hormones are also present in normal concentrations. And finally, number four, hormones may produce different but complementary results in specific tissues and organs. These integrative effects are important in coordinating the activities of diverse physiological systems. The differing effects of calcitriol and PTH on tissue involved in calcium metabolism are an example. When multiple hormones regulate a complex process, it is very difficult to determine whether a hormone has synergistic, permissive, or integrative effects. So next we'll consider three examples of how process is regulated by complex hormonal interactions. So growth, the response to stress, and behavior. So several endocrine organs work together to bring about normal growth. Several hormones, GH, thyroid hormones, insulin, PTH, calcitriol, and reproductive hormones, are especially important, and many others have secondary effect on growth. The circulating concentrations of these hormones are regulated independently. Every time the hormonal mixture changes, metabolic operations are modified to some degree. The modifications vary in duration and intensity, producing unique individual growth patterns. The effects of GH on protein synthesis and cellular growth are most apparent in children. GH supports their muscular and skeletal development. In adults, growth hormone helps to maintain normal blood glucose concentrations and to metabolize lipid reserves in adipose tissue. GH is not the primary hormone involved, however. An adult with a GH deficiency but normal levels of thyroxine or T4, insulin, and glucocorticoids will have no physiological problems. Normal growth also requires appropriate levels of thyroid hormones. If these hormones are absent during fetal development or for the first year after birth, the nervous system fails to develop normally, and developmental delay results. If T4 concentrations decline later in life but before puberty, normal skeletal development does not continue. Growing cells need adequate supplies of energy and nutrients. Without insulin, the passage of glucose and amino acids across plasma membranes stops or is drastically reduced. Parathyroid hormone and calcitriol promote the absorption of calcium salts from the bloodstream for deposition in bone. Without adequate levels of both hormones, bones can still enlarge but are poorly mineralized, weak, and flexible. For example, rickets is a condition that typically caused by inadequate calcitriol production due to a vitamin D deficiency in growing children. As a result, the lower limb bones are so weak that they bend under the body's weight. The presence or absence of reproductive hormones, so androgens in males and estrogens in females, affects the activity of osteoblasts in key locations and the growth of specific cell populations. Androgens and estrogens stimulate cell growth and differentiation in their target tissues, but their targets differ. The differential growth induced by each accounts for gender related differences in skeletal proportions and secondary sex characteristics. Any condition, either physical or emotional, that threatens homeostasis is a form of stress. Specific homeostatic adjustments oppose many stresses. For example, a decrease in body temperature leads to shivering or changes in the pattern of blood flow, which can restore normal body temperature. In addition, the body has a general response to stress that can occur while other, more specific responses are underway. A wide variety of stress causing factors produce the same general pattern of hormonal and physiological adjustments. These responses are part of the General Adaptation Syndrome, or GAS, also known as the stress response, and it has three phases. It says the alarm phase, the resistance phase, and the exhaustion phase. And you can read all about those here. So, as we've seen, the hypothalamus regulates many endocrine functions, and hypothalamic neurons monitor the levels of many circulating hormones. Other portions of the CNS are also quite sensitive to hormonal stimulation. We can see the behavioral effects of specific hormones most clearly in individuals whose endocrine glands are oversecreting or undersecreting, but even normal changes in circulating hormone levels can cause behavioral changes. For example, in precocious or premature puberty, sex hormones are produced at inappropriate times, perhaps as early as age 5 or 6. Not only does an affected child begin to develop adult secondary sex characteristics, but the child's behavior also changes. The nice little kid disappears, and the child becomes aggressive and assertive due to the effects of sex hormones on the CNS. In normal teenagers, these behaviors are usually attributed to environmental stimuli such as peer pressure, but here we can see that they actually have a physical as well. In adults, changes in the mixture of hormones reaching the CNS can affect intellectual capabilities, memory, learning, and emotional states. The endocrine system undergoes relatively few functional changes with age. The most dramatic exception is the decline of the concentrations of reproductive hormones. We noted the effects of these hormonal changes on the skeletal system when we talked about the skeletal system in 168. And we'll continue the discussion once we get a little bit further into 169. Blood and tissue concentrations and many other hormones, including TSH, thyroid hormones, ADH, PTH, prolactin, and glucocorticoids, do not change with advancing age. Circulating hormone levels may remain within normal limits, but some endocrine tissues become less responsive to stimulation. For example, in elderly individuals, smaller amounts of GH and insulin are secreted after a carbohydrate rich meal. The reduced levels of GH and other tropic hormones affect tissues throughout the body. These hormonal effects involve the reductions in bone density and muscle mass noted in earlier units. Finally, age-related changes in peripheral tissues may make them less responsive to some hormones. This loss in sensitivity has been documented in the case of glucocorticoids and ADH. Extensive integration occurs between the endocrine system and other body systems. For all systems, the endocrine system adjusts the metabolic rates and substrate utilization. It also regulates growth and development. So, as we wrap this one up, as we wrap up Module 1.2, there's some things I want you to know and keep in mind from this one. So, as insulin decreases blood glucose levels and glucagon increases blood glucose levels, this is an example of which type of hormonal action. 2, the lack of which hormones would inhibit skeletal formation. And 3, why do levels of GHRH and CRH rise during the resistance phase of the general adaptation syndrome?